Okay, so I think that's going. Now I wonder, does all this stuff actually work? There's quite a delay. According to this, I'm streaming. I don't know if I want to put my face on this. It's just going to screw me up. All right, well, I'm looking at this. I don't know how somebody found it, unless that somebody's me. So there is a chat there, so I have to figure out how to put that chat up and see whatever I'm doing with you guys at the same time. Okay, see, that's not working. So I'm sorry, I'm just trying to figure out how to do this at this point. And I would like to be able to see this screen here, as well as, since there's a chat here, I need to see the chat somehow. I'm not sure if the software will let me do that. Okay, now that's just the screen. Okay, so that's just the screen. I guess if you can at least let me know who you are, I can do stuff. All right, so here, we can minimize the me. So that I can see stuff going on over here. So okay. You know, this is just getting really weird. I don't know what that is. So I picked up this software so I can actually look at the screen here. Can I? There's a pop out. Perfect. And that's all I need. I don't really need to look at myself. Okay, so what am I doing? So this is really just a dry run. I'm glad you're here, but this is really just a dry run. And what I've been doing on Twitter here for the past couple of weeks, maybe almost a month now. No, maybe only a couple of weeks now, I think. Let's see, what was the first one? About April 20th. So, yeah, about a month now. What I've been doing is I've been trying to read 2 or 3 papers a week, really short papers, all right, that I pull out of the arXiv. So these are the 3 that I pulled out. A stringy perspective on the coincidence problem, which has to do with the Hubble controversy. That's something we're actually going to talk about on Physics Frontiers in about 2 months. It's already recorded. It just takes a long time to edit them, and right now, since we don't have a lot in the can, we've only got 2 or 3 in the can, I'd like to just do them once a month, because we're in one of these spots where I was busy for 4 months, and now Randy's busy, so getting new recordings is going to be kind of hard for the next who knows how long, right? So we'll be talking about this soon. It's already recorded. And we'll also be talking next month about something else having to do with dark stars or something like that. But that'll come out even later. That'll probably be August or September. also, if you're still listening, I'll have an appearance on something called the... Oh, it's going to kill me. I forgot the name of his podcast. It's a pretty nice title, Highbrow Drivel. I'll be appearing on the Highbrow Drivel podcast soon, I assume, if he hasn't decided that, just to cut it all off. So first was a stringy perspective on the coincidence problem on the Hubble tension. Next we have effects of a background scalar field induced by Lorentz symmetry violation on non-relativistic quantum mechanics. And I'm going to have to try to remember what that was about. So, having a privileged direction of space-time. Usually I get a little bit more in these things. Whoops. Oh, that happens to be the same one. A modification of the Schrödinger equation in a constant scalar background. And the third one is delocalization of quantum information in the long-range interacting systems, which is basically talking about the spooky action at a distance stuff. In particular, when there's an interaction with this 1 over R alpha, form, the stronger the interaction, stronger the interaction, I guess, the less of the issue is, the less propagation, or the less entanglement there is. So that's that one. So there are 3 short papers. This one's 7 pages. This one was 7 pages. This one was 7 pages. So my goal is to be able to read them in a day, them and 1 or 2 others, and then be able to talk about them here. I also wanted to, what I probably will start doing next week is I will actually read them before I do this. I was really just testing what's going on with the streaming software today, which is why it was not in any way, planned, other than, I had the idea and I downloaded software and stuff like that, just to see what was going on with this. Now, I told you one criterion, right, for choosing these papers. They're going to be short, right, so I can read 1 or 2 of them and say this was the one I liked the most. So anything that's, 126 pages, I'm not going to read that in a day. Right, so that's automatically out. There are a couple other things I'm looking for. I love, as you may have figured out already from Physics Frontiers, a snappy title, like a stringy perspective on the coincidence problem. And also, when I look at it and read it, it's actually something that's kind of interesting. So a lot of things are just sort of incremental and don't really add anything new, at least to me. So this is what I'm going to be looking at with these things. Okay, let's see. I haven't lost you. I'm scared. So let's go ahead. So I'm not sure exactly how I'll do this in the future, but I just wanted to see if we can look at some of these things. We've got the stringy perspective on the coincidence problem. This is the paper. And we can look at it. So basically we see that there's a transition in the way, there's a transition between a sort of not accelerating universe and the accelerating universe. And that's happening right now. That's this cosmological coincidence problem. Why is it that right about now, the universe is starting to expand? Why do we see something like dark energy right now, when in the earlier universe it probably couldn't have been there? And there are some answers to that here and there. Quintessence is one of them they're talking about here. And maybe they're right, maybe they're wrong, I do not know, right? But, there is a question. Anytime something just seems like it has to be picked, right? That's a little weird, right? I mean, why is it that, everything's right now? Right now, why is that happening right now? Well, anthropomorphically, you say, or not anthropically, not anthropomorphically, excuse me. What you say is, well, sometimes it just has to be now because of who we are, the kinds of beings we are, what we're made up of, and stuff like that. The universe has to have a certain kind of structure. Otherwise, we wouldn't exist. So it's possible that even though it seems like a coincidence that, certain numbers are that way, it isn't really a coincidence because, we have to exist. This is not really intellectually satisfying, right? So it's worked in the past. Weinberg's prediction for dark energy is probably the best way that it's worked, right? It's worked to figure out things, that how should something actually be, right? So Weinberg, for example, said, okay, well, we've got all this range of what the cosmological constant could be. In theory, we don't have any constraints on it in theory, but if we're going to exist, there's only a very narrow slice around zero. That dark energy has to be very, very small. The cosmological constant has to be very, very small for us to exist. And that's what it seems to be, is that this seems to be a very small cosmological constant. So he made that prediction, and then people actually found out that he was more or less right. He said it's going to be in this range, but it probably should be at the upper end of that small range. That's where we see things today. But for a lot of things, that's not really satisfying. That says, well, it has to be that way because that's what we see. However, that's not a good answer, right? That's not a great answer. That's not telling us anything meaningful about the universe, other than the universe exists in a state that we can actually live in, which we already knew, right? So you want to have a little bit better of a theory, right? This is one of these coincidences, right? We happen to be in this situation where the universe is going through a transition, and it just so happens to be just about the time we exist, right? So maybe that's good, maybe that's bad, I don't know. But I think it's okay. Yeah, I think it's reasonable to say, okay, is that really meaningful, right? And I think what this paper is trying to do, as I recall, is to try to say that we should be able to determine whether or not it's highly coincidental or sort of coincidental. So if it's highly coincidental, that's really suspect, right? We need to have some deep, meaningful explanation, right? If it's highly coincidental, if it's like 1 chance in 10 to the minus 100, or 10 to the 100, 1 chance in 10 to the 100, 1 chance in a Google, or something like that. It's 1 chance in a billion, probably. You're still going to want to have some sort of meaningful explanation. If, however, there's only a 1 chance in 10 that we'd end up in this position, then maybe it's not so bad, right? So one of the things that this paper is doing is it's using string theory to try to develop this model and figure out how long this expansion is going to last, right? And it basically says the expansion is going to last about 10 times this era we're going to be in, right? And because of that, it's not too difficult to say that we have this coincidence, right? So yeah, maybe it's a coincidence, but it's not that much of a coincidence, so don't worry about it too much. It doesn't require a lot of, I guess, what they call fine-tuning. Right? We don't want fine-tuning. We want a real physical explanation. So that was what a stringy perspective on the coincidence problem is. So I like that explanation pretty well. Not a big fan of string theory, but it worked out pretty well for this, and we'll see next week another good use of string theory to give you some interesting information. So here we have the effects of a background scalar induced by the Lorentz symmetry violation on non-relativistic quantum mechanics. So this is, like I said, a way to sort of extend quantum mechanics a little bit. Let me see, is anybody still here? Oh, wow. Okay, so, I was just going through this one as well. So what he wants to do is he wants to build a standard model extension that has a Lorentz violation in it, right? So he's written this Lagrangian, which tells us all these things. Oh, and he's got a Higgs doublet. And I have to say this, I don't really remember much about this. Unfortunately, it's got a particle in a box and some wave functions. And this is why it would be better, like I'm going to do next Tuesday, to actually read the papers directly before I do this, right? So again, this was mainly an idea to try to, just get something going, right? I just wanted to get something going, see how it actually works out this time. So he's added a standard model extension, and man, I blacked out. I'm so sorry. I thought I'd be better at remembering these things since I just read them last week. No, Tuesday will be better. I hope. And then we have the delocalization of quantum information in long-range interacting systems. This is interesting. It talks about quantum monogamy. That's something that's important in quantum information theory. Oops, that's the wrong place. So, in fact, what it's saying here, this was the 1 over RA, is that quantum isn't as monogamous as, you might think, right? So that, that might make you happy, that might make you sad, but it's not that, horrible. So, again, this is talking about all the entanglement and correlations and so forth. And, the coupling between two quantum systems is mediated by some energy, some force. And these interactions are usually given by a power law, right? So 1 over r to the alpha is the way they write it here. That's the normal way you think of a force, right? When you think of a fundamental force, at least, you've got two things. You have that 1 over r to the alpha term there that tells you how fast it drops off in one sense. But then also you're going to have a range term, right? So you have a range term if you're talking about the weak or the strong forces, right? There's a range to those forces that you're not worried about. So these guys here wanted to do something about that and try to figure out how this power law, which we should have a space there. Hopefully they'll catch that in editing. They don't always. This power law, how does that relate to the coupling, right? And they're using this tripartite mutual information. I hope that's the one they use. previously it was used by somebody else with another name that was also, instead of tripartite, it was another thing that began with T, and I've forgotten the name of the guy and I've forgotten the name of that. But basically, normally saying we have a bipartite entanglement, that's what we normally think of. If you remember that spooky action at a distance episode that we did, or the Wigner's friend, or just about anything with entangled particles, you're generally thinking of, okay, I've prepared a state. That state has 2 particles in it, and I send them away from each other. And then there are correlations that when I make long-range detections with them. All right. And so, in some sense, the quantum information is delocalized, right? It's the information isn't all about this guy, and it isn't all about this guy. It's about the 2 guys together, right? Not too horrible, right? But now he wants to put 3 things together with this power law to see what actually happens, right? So here's sort of a way to look at those things in terms of sets, right? If you're going to look at sets with a normal, so if you're going to look at these Venn diagrams, these are just Venn diagrams. For normal probabilistic stuff, you can use these to directly write probabilities, right? That's why they teach them in that 100 level descriptive statistics class that you may have taken. Or hopefully you didn't. I was in a faculty meeting and we were discussing that, and I said, when I first went to college, I knew I wanted to do physics. So I knew that quantum mechanics had something to do with probabilities. So right away I took a statistics class that I could take, my first semester of college. And it was the worst mistake of my life because, sort of the level of the descriptive statistics class is so low it doesn't really help you understand very much, not only about quantum probabilities, which are different, that's what Bell's theorem says, but it also doesn't really give you much of an idea about what's going on in probability either. So until you get to the 300-400 level courses, you're not getting too much information, more TMIs. All right. So here is your normal sort of thing. We're going to look at a von Neumann entropy. It's talking about mutual information. You have that S. S is very suggestive because, just look up here at equation 1. It's basically the entropy, right? You have entropy for information. You have entropy in physics. Here we're looking at entropy for information, right? So we'll look at something like this. And correlations also have something like this, which is more or less the same thing. It's more like, this is basically like the variance, or the covariance, in statistics. But he wants to actually measure it. Oh, topological entanglement entropy was the original name. So he wants to test this the same way you test this in like the aspect experiment, like you test it in Bell's theorem, right? You're going to say, okay, well, when I do my experiment, or in this case it's not an experiment, but he's going to build something up like Bell. When I do my experiment, what do I see? Do I see something that looks like the classical information, or the classical information, or the quantum information? And what do you think he's going to find? Right? He's going to find it's with the classical information, right? So here's the Bell-like theorem right there. The information of A given B and C is greater than the information of A given B plus the information of A given C. And he's going to see how that looks as he changes the interaction. So you're going to do a little bit of numerical work probably. I've forgotten, but you're doing a lot of this stuff too, this math. But what he wants to do is he's going to change this A, right? This alpha, excuse me. I hate it when my students do that. Right, here we go. And this is going to tell you how much information is lost. And that's what he's done here. Here he's got two different, let me zoom in on those. This is the reason why I wanted to do this. It's also the reason why I don't end up with, I haven't put things up on YouTube for the podcast for a while. Well, it's one of the two reasons. One is I want to put in these diagrams, right? And the other is I want to re-edit a lot of the old, maybe not so old even, audio, because they're not so great sometimes, you know. So here we have that range, right? So we have 1 over r to the alpha is the strength of the power law. So if this is an energy, because it's quantum mechanics, that would normally be like 1 over alpha, r to r, just 1 over r. So alpha would be 1 right here for electromagnetism or for gravity. You can get gravitational oscillations and interference in standard quantum mechanics. And they've done the experiment, right? And here you have the time, right, as it goes on. And if I was smart, I would have looked up what J0 actually means. That's the reference time in some sense. So I really want to know what that is before I made too much of this. So this is saying that you've got, you know, quite a lot of correlation here, and then it dumps off, right? And then he's going to put slices here, right? So he's got slices for different, so each one of these different colors. I think those are alpha increasing. Let's see here. Yeah, so alpha increasing from 0.2, 0.5, 1, and 3.0. Okay, so this one right here is what he's getting for like electromagnetism, electromagnetically coupled atoms or objects. He's looking at this shared information and this mutual information, tripartite mutual information. And basically what you want to remember is that if this thing goes above this 0 here, you've got sort of a quantum violation, right? And as this stuff decreases, as the really looking at this peak, because, you know, for each one of these, when you're doing this simulation, you get a drop off after this correlation time J0. But as you decrease the strength of the force, right, or as you increase the drop-off rate of the force, so this is a hard thing to say. What you see is this increase in this peak, right? So for the 0.2, you basically see nothing, so you don't really have any violation of, you know, the mutual information Bell's-ish theorem. Not really Bell's theorem, but Bell's-ish. It's a similar kind of theorem, except for, of course, this mutual information. Here you start to get that violation. That violation means, obviously, it's quantum mechanical. So you drop off more, this 1 over the square root of r, and you start to get a little bit of these correlations at long distances, which you could not get classically. And then you go to 1 over r, our normal thing, with a electromagnetic interaction, and you get a pretty large one, and you get to 1 over r cubed, even larger, you get a larger violation up here, although for a shorter time. Okay, so this inset is just this expanded. So that's what's happening. So you're seeing what he's saying, right, is that the faster your interaction drops off, the more sort of non-local correlations you get, right? So that's really, really interesting. That's really, really clever. And he's doing this with a spin chain model, right? An Ising model, sort of, maybe not an Ising model, but, you know, or I guess it was an XY spin model. So that's sort of normal sort of thing that people who do that sort of things do. So this is very important for quantum information theory, for quantum computing, and that sort of thing. So that's more or less what's so interesting about this thing. So I don't know. Maybe you think that's interesting that, you know, with the stronger drop off, you get more of this kind of thing. Actually, I find it quite interesting. So that was a really interesting numerical study, and I liked it quite a bit. So thank you very much for showing up. I'll try to do this again more or less, I don't know, every Tuesday. If you look at the stuff in on Twitter, that's where I'll be posting these. So on Friday afternoon, you'll probably have all three of them for next week going on. So right now, I don't even know what those are, right? Also, if you have any other questions about the podcast or anything like that, go ahead and you know, put them up here. That's part of what I want to do here, right? Is I want to look at what's actually interesting to you and answer some more questions and stuff like that. Oh, there's that guy's podcast right there. So let's see, what did I pick out so far? Oh, the elastic vacuum. Oh, I like both of these. And the bounce of nothing. Okay, this is a really interesting one. Oh, this is the one with the Hubble tension. He's answering all sorts of questions by looking at fuzzballs, right? And this one, the bounce of nothing, is an interesting one where they're talking about, you know, little bubbles of nothing appearing in space-time, right? And that is going to explain sort of dark energy, and they find a minimum size for those compactified dimensions in string theory, right? So that's really interesting as well. So I like both of these. These guys are both string theory things, a little out of what we normally talk about on Physics Frontiers, but they're very interesting, and hopefully there'll be another really interesting one when I, you know, go to work tomorrow and print something out to read with my morning coffee, right? Anyways, that's what I've got for today. This seems to have actually worked. It would be so yeah, this worked. I like it. It seems to be okay. If you would like to see anything in particular or have any other questions, you know, go ahead and leave me questions. You can leave me questions here. You can leave me questions at the Patreon, right, where I think the way I did this, hopefully I'll find out, this was done through the Patreon. And you can leave me questions, you know, on the website, frontiers.physicsfm.com, and I'll check all those things out before I do the next live stream. So I guess thank you very much, and I hope you have a really great day.